Welcome back to the Python tutorial series for Climate Mathematics Theory and Applications. In this video, we will continue to cover Chapter 2, Basics in Python Programming, namely reviewing vector and matrix computations. Let's begin with creating a 5x1 matrix. We are going to be doing this by accessing the NumPy module with the mat function. In order to use the mat function, we need to create an array of arrays. So we have our outer array highlighted, and we have 5 elements as the elements of our outer array. And notice each element of our outer array is an array of itself. This creates a 5x1 array that looks like the outputted matrix in line 25. We have seen in previous videos that you can create a sequence quite easily using Python's np-arrange function. We have a start value of 2 and an end value of 7. Just a reminder that 7 is not included in our sequence. We end at the point before our end sequence, giving us the array of 2 through 6. Now let us create a sequence that is incremented by 2 that ranges from 1 to 10. So we have a start value of 1, an end value of 10, and an increment of 2. So we are going to be starting with our value of 1 and then adding 2 to every increment, which gives us the array 1, 3, 5, 7, 9. We're ending with 9 right here because that is the value that follows our incremented sequence that ends before 10. Now let's create a 4x1 matrix and let's name it X. Our 4x1 matrix is a column matrix of 1, -1, 1, -1, seen by the internal structure of our np.mat function. Add 1 to each element of X using this function, x plus 1, and wrapping it in a print statement. This actually isn't modifying x at all, but it is allowing us to see what x would look like if we added 1 to each element, giving us the value, the matrix of 2, 0, 2, 0. You can also multiply each element by 2 as seen in line 29, which gives us the values of 2, -2, 2, -2. Similarly, you can divide each element of x by 2, seen in line 30. We're going to jump to line 31, where we're going to be creating a 1x4 vector with a sequence incremented by 1, ranging from 1 to 4. We're going to be using that np.mat function with an np-arrange function on the internal structure. We're going to start our sequence at 1 and end it at 5. Just remember, 5 is not included in this sequence. We are ending at the value before 5 that follows our incremented list. We are going to multiply each pair of elements with our x vector that was created above. Just a reminder, our x vector is a 4x1 matrix with the values 1, -1, 1, -1. And our y matrix is the 1x4 vector that has values 1, 2, 3, and 4. So when we multiply our x vector times y dot t, which is defined as the transpose of y, we do in fact get the matrix outputted in output 31 that has the values of 1, -2, 3, -4. You can also do computations like dot products. If we were to go ahead and access the NumPy package and utilizing the dot function, we can find the dot product between X transpose and Y transpose, which gives us the matrix, the singleton matrix of -2. Next, we will be transforming X, which is a 4 by 1 column vector, into a 1 by 4 vector. We are going to transpose X with that dot T notation, and then we will be finding the shape of our transformed X, which gives us a shape of 1 by 4. 1 being the rows, 4 being the columns. So X dot T is truly a 1 by 4 vector. In line 34, we illustrate a simple dot product between vector Y and matrix X, and we do get the value of -2. We can also do matrix multiplication, which is the Cartesian product of two matrices, seen by the mat-mul function that is accessible in the NumPy module. We are going to do matrix multiplication on X and Y. When we do the matrix multiplication for these, we do get a 4 by 4 matrix with the values that are highlighted. Line 36, we can see that we are defining my as the y vector that is going to be reshaped into a 2 by 2 matrix. This reshape function does help us convert a vector of values into a matrix of elements. With the same notation as our shape, we do have a row by column. So we will be transforming Y into a 2 by 2 matrices. Following this reshaping of Y, we are also going to be transposing Y. Just a reminder that the dot notation that Python uses is incremental, meaning that we will access Y, then we will reshape Y, and then we will transpose Y. Python does follow this type of hierarchy when using that dot notation. If we want to go ahead and print the variable my, we do get the matrix 1, 3, 2, 4. Let's go ahead and find the dimensions of our matrix using that dot shape notation. We do truly get a 2 by 2 matrix outputted of the my matrix. If you wanted to convert a matrix back into a vector, we can use the dot flatten function. Dot flatten will allow us to convert all of our rows into one row, as seen as the output in 38. We now have a matrix of 1, 3, 2, 4. So we are basically taking the bottom row of our my matrix and flattening it into a 1 row matrix. Moving into line 39, we are going to reshape our X vector into a 2 by 2 matrix. We are going to name this mx. So we're going to do X. We are going to reshape it in a 2 row vector. This -1 notation doesn't mean that we will have a negative one column by any means. This just allows Python to fill our two-row matrices appropriately. We are then going to transpose our x.reshaped matrix to finalize our mx variable. We are now going to do a computation multiplying each pair of elements using the NumPy module accessing the multiply function. We are going to be multiplying each pair of elements between mx and my. When we run line 39, we do get an output matrix of 1, 3, -2, -4. We can also do division between each pair of elements with our np.divide method. If we wanted to divide each pair of elements between mx and my, we do get the output matrix seen in out 40. Next, we will be subtracting 2 times a matrix from another matrix. We are going to be doing this with the NumPy method subtract, which is highlighted on the screen. You are going to have your first input as your first matrix. Then you are going to do some simple arithmetic on your second matrix, and that is going to be your second input. This subtraction gives us the highlighted matrix. The np.matmul matrix multiplication function is the normal matrix multiplication found in linear algebra. We are going to be doing a matrix multiplication on mx times my, which gives us the output as seen in line 42. We can also find the determinant of a matrix, which is highly useful in many industries. We are going to be defining x, the NumPy module. We are going to access the internal package of linear algebra, LINALG, and further accessing the det method. The det method is the determinant method. So this line of x will find the determinant of the my vector. When we go ahead and print x, we do get a determinant of -2, which you can check algebraically or on your paper. Python also allows us to find the inverse of a matrix, once again utilizing that linear algebra package that is within the NumPy module. We need to find the inverse just using a simple I and V method, which we define as z in this case, and then when we print z, we do get the inverse matrix of -2, 1.5, 1, -0.5. We're going to set A equal to the matrix multiplication of z, which is the inverse of my. When we do this matrix multiplication, we do get an identity matrix out, which verifies that z is truly the inverse of my. The next function that we are going to use will return a left to right diagonal vector of our matrix. We are going to utilize the NumPy package with the diagonal method. So the diagonal of my is going to be the array 1 to 4. In order to return eigenvalues and eigenvectors of any matrix, we will be go ahead and accessing that linear algebra package in use with the eig method. We are going to be setting my eigenvect equal to the ig of my. When we print this newly labeled variable, we get an array of 2 elements and a 2x2 matrix output. In order to hash out what the array and what the matrix means, we need to go ahead and define what these mean. The array that you are getting outputted by your ig method, these are going to be your 2 eigenvalues that correspond with your my matrix. The matrix that you get out is a 2x2 matrix that contains the eigenvectors of the my matrix. Next, we can go ahead and find the singular value decomposition, or more commonly called SVD, of the matrix. We are going to access SVD method through the linear algebra package, and when we do such things, we are going to get a few things that are exputted. We have the first exput is going to be a 2x2 matrix. The next is going to be an array of values, and the last element that is exputted is another 2x2 matrix. Next, we will be going into how you can solve a linear matrix using a linear equation. So we are going to set ySolve equal to the NumPy linear algebra solve method on my with a solve equation of 1, 3. So what this is saying is we are going to multiply my by some vector x, and you should be able to get an exput of 1, 3. If we were to go ahead and run ySolve and print it, we do get an array of 2.5, negative 0.5. If we were to go ahead and multiply my times this highlighted value, you will in fact get a vector of 1, 3 outputted. We can verify the solution in line 49 by doing another matrix multiplication in between my and ySolve. If we do matrix multiplication between these two matrices, we do in fact get our original inputted array of 1, 3 outputted. With that, this concludes Vectors and Matrices section of Chapter 2, Basics of Python Programming. In the next video, we will continue to cover Chapter 2 and finish off Chapter 2 talking about simple statistics in Python. Thank you.